Hello and welcome to Explaining Rust Analyzer, a video series where we try to understand how Rust Analyzer works one crate at a time. So, where are we at right now? We've spent a lot of time before covering various surrounding things around the core of the compiler. We talked a lot about the underlying source infrastructure, the underlying sources of data, the crate graph, source routes, source files, all that stuff. We talked a lot about parsing infrastructure, and last time we covered micro-expansion infrastructure a bit. Basically, we didn't look how micro-expansion actually works. We only discussed that it functions on top of token trees. So you go from a syntax tree to a token tree, then you do micro expansion on the token trees, and then you convert the token tree back to a syntax tree. So today we will continue looking into the actual compilery bits of the compiler, and in particular, today we will start finally discussing the meat of it, the HirExpand crate. So let's go to this crate. It is right here. And that's kind of an interesting crate. So it is the lowest level of the compiler. It doesn't contain a lot of logic by itself, although today it contains actually the implementation of various built-in macros. But the main thing it does, it defines the core data structures which compiler uses to reason about things. And the first such data structure we will be covering is AstIdMap. And yeah, that's a cool thing. So basically, when you are compiling stuff, you have functions, structs, parameters, and you need some way to refer to those things. You need to be able to say, hey, I'm talking about this struct. The type of this struct is this, and the struct has these fields. So you need some way to give identity to things. If you are writing just a traditional command line compiler, then the easiest way to give this identity is to use an object identity. Basically, if you write your compiler in Java, you can have class struct, and an instance of that class would actually going to be the struct itself. It's placed in the logical model of code. In Rust Analyzer, because we have this laziness thing and we have this evolution over time thing, we cannot just use a single identity, because there is this struct before you edit the file, and then you edit the file, and the struct is kind of the same but kind of different. So specifically, I don't know, let's say that we have this struct, and let's say that we add foo field here. So it's kind of different because the set of fields is now different, but it also kind of is the same because we want to assume that the API of the struct doesn't change. So we need some way to kind of say what is even the thing we're talking about. And the core idea of identity we use in Rust Analyzer is actually positional. Basically, we are saying that, hey, what is this struct? Well, this is a struct in crates HirExpand src AstIdMap.rs file, which is situated on the line 20. So that means this across any revisions, if I start typing things here, then this struct continues to be the same. But if I say move this struct to some other file, then it would be considered a different struct. And this file AstId is kind of like a part of what allows us to identify like this locational identity of a structure. The simplest way you can refer to the location of a structure is to use a pair of name of a file and the text range of a struct inside of a file. So we literally say that, hey, kind of like this struct is in this file on lines between 20 and 23. The problem here, though, is that such position-dependent locations are very volatile. Basically, if I start typing a comment here, I shift all the offsets in the file. And that means that in this revision with the comment in, this structure will have a different identity. And that is problematic because we want the same things to retain their identity so that when we do incremental compilation using Salsa, we can actually reuse more of the type information. We want to assign an identity which doesn't actually depend on a physical location of a struct inside a file too much. So that, for example, if we add a new comment, like the location stays the same. And the idea we use here is that if we have, let's create a new file. Let's say we have like a file like this. Basically, we say that the struct bar is the second structure in this file. So we use kind of like relative position of things that matter in the file as, well, a position. So basically, here we get something like foo 0 bar1 bars2, and that mapping is obviously independent of us adding like fields or like functions or something like that. Of course, if we now add a struct new here, it will shift all the indexes. But the edits where you add a new top-level item are relatively rare. And for those edits, we are going to have to recompute everything. Well, not everything, but a lot of stuff anyway, which we will cover in the lecture about name resolution. So that's like an okay strategy. A better one would actually be to the problem here though is that if we just kind of like swap two structs in a file, then the IDs got swapped, which is like less than ideal, and we would like to understand that, hey, like this is the same. So what you could do instead is that you can also add a name of a struct to its identifier, so it's like not the third struct in a file, but a third struct in a file with a name foo. We didn't do this optimization yet. And yeah, it's kind of like non-trivial because you like, if you have two structs foo in a file, it's obviously an error. It's a compilation error. You shouldn't have two conflicting names, but we still need to be able to represent this in a logical model. So you cannot use just the name of a struct as its identifier. Okay, so what is the algorithm for assigning these numbers? Well, first of all, we actually want to assign these numbers to all the things which matter. So we want to assign this to structure, we want to assign this to functions, we want to assign these identities to modules, and to nested structs inside modules as well. But, for example, we don't want to assign this identity for expressions and statements, because that would be like pretty useless, basically. We only want this for top-level visible items. And the general idea how we do this is that we just walk the syntax tree and note the order in which we visit items, and then say, hey, this ordinal number is actually the index. But there's a couple of twists on top of it. So yeah, let's look at how this actually works. So this is file AstID is an integer identifier of a specific AST node inside a file. Internally, it stores a raised file AstID, which is an index of a syntax node which doesn't care about its AST type. Because remember, our typed AST is backed by untyped syntax tree nodes. And the whole mapping is stored in this AstID map. So basically here we store an arena, essentially a vector of pointers to all the items. And the idea of the item is just the position of a syntax node of this item in this vector. And let's look at the API first. So you take a syntax node and you get back an AstID map. Then given a node in this given constructed map and a particular syntax node in its file, you can get its file AstID. And finally, if you have a mapping and you get an AstID, you can get back a syntax pointer, which you can then use to get to an actual syntax node. If you remember, AST pointer is a wrapper around syntax pointer, and its main API is that you take a pointer to AST node, you give it a root file, a root syntax node of a file which this pointer originated from, and then it returns you a specific AST node there. So yeah, that's the crux of the API. And again, kind of like the trick here is that AST pointer and syntax node pointer essentially store ranges inside, so they change every time you do any kind of modification inside a file. But these file AstID things, they store only indices in this arena, and they generally stay the same. Yeah, they generally stay the same across minor modifications like adding comments or whitespace or just editing bodies of the functions. So I guess the most interesting thing is probably this get method. Yeah, it's just looks up using the index in the arena. Then actually I wonder how we do this. How we actually get ID. Oh wow, that's interesting. So to go from a syntax node to integer ID, we just do a linear lookup through all the items, which actually feels pretty slow. It definitely could be made faster if, in addition to this arena, we just store like the sorted mapping back from syntax pointers to indexes. Like that's kind of like fix me. Does it matter that this is so slow? Okay. The final thing which is left is how we actually construct this thing. And I kind of like talked about this. We walked the syntax node, walked the syntax of the file, and for every interesting node, which is in our case an ICD item, things like const, enums, blah 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 blah, basically like all the top level things, but also like, and that's kind of like important, macro calls, because you can say something like foo bank on the top level, and that is considered an item. So items include macro calls. Okay, so we walk the tree in a particular order, and if we notice an item or a block, we just push it to our arena, and a log is like some trivial wrapper. It's just like pushes this item to this arena object. Yeah, I don't think we've looked at the arena before, but just like to make sure, it's literally just like a vector of items with some meta typing on top of it. Yeah, and like one curious thing here is about like what is the traversal order we use for files, and it is like BDFS thing, which I kind of like come up with. I don't know, maybe it's like used somewhere else, but don't think I've seen it elsewhere. And like the idea here is like when you typically walk the tree or walk the graph, you use either breadth first search or you use depth first search. In this thing, we kind of like combine the two. So what the hell is going on here? If you look at something like this, let's say we have a tree of modules like M1 and M2, and those have like some functions in them. So you actually want to assign IDs to modules as well as the functions. And ideally, what you want is that when you add a function inside a module, so let's add something like S here, you don't actually change the ID of this module. So if you add a function S before function F, then you kind of want to change the ID of function F, but you don't want to change the ID of module M. And that motivates our depth first approach. Well, no, breadth first approach. So when we walk the file, we first visit top level items, M1 and M2, and those get IDs like 0 and 1. And then we recurse inside this. So F goes ID 2, and G gets ID 3. And then when we add function S here, well, the S will get ID 2, the F will get ID 3, and the G will get ID 4, but M1 and M2 will stay the same. The problem with breadth first search order, though, is that when you traverse the tree, you need to keep a queue of elements which you are yet to visit. And that's kind of like a frontier of your traversal. And given that syntax trees are pretty shallow and pretty broad, they have high branching factor, that frontier actually means that at the limit, it will contain every leaf of a node. So basically, the length of the frontier is proportional to the total number of nodes in the tree. And the total number of nodes in the tree is actually much higher than the number of nodes which we are interested in, because we are interested only in items. And we don't care about like a fun token. We don't care about this parameter list. We don't care about, well, we do care about this block, but if there is some expression inside, we don't care about this expression. But if like this expression is actually like a block which contains function foo, we do care about this nested function. So we kind of like want during our traversal like quickly skip through expressions, but still touch each and every item. And yeah, that's why in this traversal basically we use a DFS, but we only enqueue items which actually get IDs. So only if our callback here returned true, we actually enqueue this in the work queue, and we skip traversal. And when we actually pop an item from our work queue, we start with usual depth first order. And that means that like the size of our queue right now is only proportional to, well, the number of items and not the number of whole expressions. And that is important because this all is backed by row1. And if you recall, the idea of row1 green tree, red tree is that if you hold on to a node, then you implicitly hold on to like the chain of parents. So while you're traversing the trees in row1, you generally want to hold on to as few nodes as possible. And if you do a breadth first traversal of a tree, that means you have to materialize the whole red tree in memory, while you typically want to materialize only one path from the top node to the current node. That's why like this switch makes sense. So that's was like probably a bit more detailed than the rest we are going to than the rest of what we are going to talk about today. But anyway, still kind of like a cute little algorithm. So to sum up, AstIdMap allows us to assign stable identity to an items inside a single file. So you create AstIdMap, and using AstIdMap, you can convert between syntax node or syntax pointers and file IDs, where file IDs are guaranteed to stay stable across modifications. File ISTID is actually a part of ISTID. So file ISTID identifies a single n in a specific file, while ISTID identifies like any n in any arbitrary file. And basically it is like a pair of file and this file ISTID item. And this in-file thing is actually a type which is used throughout rationalizer code base. It's like the basic thing which allows you like to identify something. It is a pair of a specific file and like anything, which is in our case file local ID. So and this brings us to HirFileId. Again, kind of like the one of the most interesting and important types of rationalizer. So yeah, here we need to talk about files. If you recall a lecture about source database, there we had a concept of file ID, which is basically a file in a virtual file system. And we had an ability to get file text and file syntax tree. Here we use like this HirFileId, which is represented either as a raw file ID or as a macro file. And that's pretty important. So when Rust Analyzer sees macro invocation like foobank or like macro invocation like actually any of these derives, what it does is that it creates sort of virtual file for the result of macro expansion. Let's use a concrete example here. So here we have macro, and we invoke it. We can actually ask Analyzer to invoke this macro. Let's actually make this more interesting to see that we actually do the expansion here. ID. Okay, yeah. Now that's a bit more interesting. And essentially, Rust Analyzer treats this macro expansion as a virtual file. And while, say, this M macro is defined a usual file, like a file which has file ID, this bar function, it still exists. But it exists in a file which was generated by macro. So its file ID is represented by macro. And let's look how it works, because it's actually tricky, because first of all, like the code here is like rather convoluted because we need to support all kinds of macros. The core idea is much simpler, but even the core idea is pretty neat and needs some time to wrap your head around it, because it actually makes the representation of macro files recursive. If you recall, I said that macro invocations are actually items. So macro invocations, each macro invocation, each like mbank has AstId. That is a pair of file where it is defined, plus the like index of this macro invocation inside this particular file. And we say that, let's actually write this. Simple here. File ID, it's either like text file or a macro file, where a macro file is identified by macro call ID. How can I disable this? And like parent. Yeah. So that is like the recursive structure I'm talking about here. So that's like how file IDs look in Rust Analyzer. We are either in the original file written by the user in a text file, or we are inside a macro file, which was generated by a macro call in some specific file, where that specific file might have been generated by the user, or it might have been generated by the macro. But again, that's kind of like a simplification. Let's look at how the thing actually looks. So first of all, HirFileId is opaque. We deliberately don't want to care where the files are macro generated or generated from a source text. So we hide the internal representation. That said, internal representation is either a file ID or a macro file, where a macro file is identified by a macro call ID. And macro call ID is like slightly trickier than what I've described before. First of all, it goes via this salsa interning infrastructure. So you see that there is like an impl intern key here. What this basically means is that this macro call ID is just an U32. But this U32 is actually the third index into a table which contains these macro call locations. So macro call ID essentially contains this information, but compressed to a single U32. And compression matters for two reasons. First of all, well, we use this ID a lot, and we really want it to be like a compact thing which we can actually refer to. The second reason is that, well, this thing is actually recursive. If you remember in Rust, when you define a recursive enum, you actually need to put box somewhere in there to make the size of enum actually finite, and that is essentially what is happening with this internal Slasa database, except that rather than like doing this box, I think we do an indirection via internal table. Because again, we want to compare to macro call IDs, and we want to put macro call IDs as keys in a hash map. And for that, you really benefit from it being just a single integer rather than a deep tree-like data structure which you need to compare recursively. So, the main thing macro call ID contains is what I showed you, the AstID of macro call. To remind you, AstID is file local AstID plus this HirFileId. So again, kind of like AstID contains HirFileId, and HirFileId contains wrapper, which contains macro file, which contains macro call ID, which is essentially macro call log, which contains macro call kind, which contains AstID, which is like, again, so you see like this loop of mutually recursive things. And yeah, that's hard to wrap your head around. Okay. Yeah. So this contains macro call kind. It's interesting that we in macro ID we actually like at least in the first iteration, that's actually what was there. We just identified macros by the position of the macro invocation. The crucial thing we have now here is that we also encode the definition of the macro into this location. So to give an example, so let's say we have some macro foo, and let's actually do this slightly. Can't type today a slightly longer example, so it doesn't necessarily compile fully. Okay. Okay, something like this. So here we have, and let's actually make that meaningfully different. Yeah. So here we have two foo macros, one in M1 module, another in M2 module, and here we like call this foo macro from M1 module. And the interesting thing here is that macro call location for this call includes not only information about the location itself, but it actually encodes which of those foos we are talking about. So if we change this from M1 to M2, this macro call ID would actually be different. And that's like pretty crucial, and that's what makes Rust incremental computation actually work. I guess I will cover this specific thing closer when we will be discussing name resolution, but right now just like like put this somewhere at the back of your mind that like we do something strange here. Rather than use an application on the call ID, we also encode the resolved macro we use to expand this specific macro invocation. So yeah, I guess that roughly is what I wanted to talk about here. Let's now look at the definition of the AstID database. That's like actual Salsa database, which is defined in the script. It has like a bunch of queries actually, and most of those queries are about macro expansion, and they're kind of like technical and non-interesting. So today I want to like discuss only like the first two queries, which are actually the most important ones. So parse or expand. This thing takes HirFileId and, well, parses it to a syntax node. And it works in a like rather predictable way. If the underlying HirFileId is actually a physical file, it is parsed directly using this function from a source database we seen earlier today. If it is a macro file, we parse macro expansion, and like that's a little bit more involved. Like it contain like this bit of code contains like this logic for conversion from syntax trees to token trees. So you see that like we want to parse this macro file, and first we expand it, and what we get is actually a token tree, and then we actually parse this token tree back to syntax, and then we return the syntax, and also there's like a huge amount of error handling here. But like, yeah, I guess like the details are not important. The main thing here is that, yeah, we just like expand this macro. And yeah, that's the kind of like parse or expand. And like this is like the entry query for more or less every compiler functionality, because to start analyzing the source code, you actually like need to get a syntax tree corresponding to the source code. So you start with a specific file you want to analyze, and then you parse it into the syntax node, and then you do analysis. And then the way you do analysis, you actually want to say what kind of structs or functions were contained in this file, and like you want to record the types of those things. And for that, you need to be able to refer to identities of those things. And here comes the second important query in this database. This is AstIdMap, which takes your file ID and returns you an AstIdMap, which you can then use to get integer IDs, integer stable across your parsing IDs for specific syntax nodes. Okay. I wonder if like do we want to actually look how macro expansion works in more detail? Yeah, actually, let us trace this just a little bit so that we understand the general flow of information. Like the tricky bit here is that, well, macro expansion is complicated. In particular, there are like many kinds of macros. There are declarative macros, derived macros, procedural macros, built-in macros, eager macros. And I want us to look only at the macro by example, declarative macro case. So let's do this again. We want to parse this file, and it turns out to be a macro file. So we call parse macro expansion, and macro file contains this macro call ID. So first of all, we call macro expand, which takes this macro call and returns its token tree. The way we expand a macro call is first we convert ID to the location, and this we are going to ignore. Then from this location, we want to get token tree corresponding to the input of the macro. So if we are writing something like this, we want to get the token tree corresponding to this thing. And this is done by the macro arg function, which looks at the syntax node of a token tree and then converts that syntax node to abstract token tree representation, which we were talking about last time. And to get the syntax node, we again look up a macro location. Oh man, it's very complicated. Well, it's not very complicated. It's very annoying. We look macro location and we look at the kind of macro. And declarative macro are represented like a fan-like kind, where we have AstID of the macro call. So for that, we actually take this AstID of a macro call, and using it, we get the syntax node corresponding to this AstID. And this is actually the bit where we hit the recursion. So again, kind of like, what is happening here? We are processing code like this, and we want to get a token tree for this thing. We have the ID of this macro, which is essentially a pair of the parent file and the location of this macro call in the parent file. So we take this ID and say, hey, please give us the actual syntax node corresponding to the macro expansion. And here we need to recursively parse the parent file compute AstIDMap for it, extract the particular syntax pointer for our call, and dereference that pointer using the parsed syntax for the parent file. So like not only HirFileId is recursive, the whole macro expansion process is recursive, because to expand the macro, like you need to get its text at least, and to get its text, you need to get the file where this macro call is placed. And that file might actually be a result of some other macro expansion, so you gotta expand that as well. Okay, so we got the syntax node corresponding to the macro call. We converted that to the token tree. Then we look up the actual transformation from a token tree to a token tree using macro definition, which is encoded into macro location. We used that, so expander is basically a map from token trees to token trees. We use this expander to compute the resulting token tree, and yeah, that's the token tree which we are going to return here. Okay, it's like So this is the token tree we get here, and then we like convert this token tree back to syntax tree. So yeah, that's like pretty nasty, pretty complicated, pretty convoluted, and definitely very recursive code. But luckily, if you are not working on the macro expansion itself, you don't need to understand it. The only thing you need to understand is that files in Rust Analyzer can originate either from text written by the user or from macro expansions. Files are identified using here, file ID type, which is an opaque identifier of a file. And given a particular file, you can actually identify a specific syntax node inside this file using AstIdMap or AstIdMap and AstId. And the primary benefit from this roundabout recursive identity thing is that the resultant IDs stay the same across many modifications. So in the end, like this trait has some identity in the database I have in Salsa right now. And if I add a new method here, then obviously the state of database changes, and like this actual trait changes, and the trait in the new revision is not actually identical to the trait in the old revision because, well, it has one new method. However, it has the same ID. So this sameness of ID will allow us in future lectures to effectively reduce results of various computations. Okay, I guess that's it for now. Again, sorry for like this lecture being kind of like very hand-wavy and like very confusing and very recursive. It's just indeed just like the product of two things. First of all, like macro expansion itself is like a lot of like accidental complexity. I think like probably could just like write this particular code better so that it reads nicely, because it's just like very convoluted with all those cases. But there is also like very core of this recursive definition of macro file ID, which is indeed complicated, and indeed like there's like no way to make that simpler. At least there is no way known to me to make that simpler. Okay, so despite all this complexity, now we are actually in the good shape where we can parse source code and we can actually meaningfully speak about things in the source files. And that sets up for actually starting making analysis of the source code and doing some kinds of semantic inferences. So thank you for watching, and see you next time.